Hello, AP Chemers. Hope you're having an amazing day. We're going to continue our notes with calculations with the equilibrium constant. Some of you, we've already done this one with the NOCl. Some of you are about to start this one. So I'll go over this one again just in case, but if we already covered this one in your class, you can go ahead and move forward to the next one. So we want to calculate K at 25 Celsius for the decomposition of NOCl. We're given that we have 2 moles of the NOCl in a 1-liter flask, so it's 2 molar. And then it's allowed to sit there and reach equilibrium. And in the equilibrium system, the concentration of the NO is given to us as 0.66 molar. So first thing you want to do as soon as you see equilibrium is write the KEQ expression. So KEQ is equal to the concentration of NO squared times the concentration of Cl2 over the concentration of NOCl squared. Next, we're going to plug in our values. So we're given 2 moles of NOCl and it's 1 liter. Problem is, we can't plug that in here because these have to be the concentrations at equilibrium. In the question, it tells us that 2 moles of the NOCl are placed in the 1-liter flask, and then it's allowed to reach equilibrium, which means that the 2 molar, that's your initial concentration, not the equilibrium concentration. So, excuse me, if you don't have the equilibrium concentrations, that means you have to find them out some other way, and that way is usually an ice chart. So to do an ice chart, you write out your equation, so 2 NOCl yields 2 NO plus Cl2, and you write ice next to it. Ice stands for, the I stands for initial, C stands for change, and E stands for equilibrium. So basically, an ice chart takes you through the reaction. Initially, you can do this in concentrations like molar or in moles, but you put your initial concentration, so at the very beginning of the reaction. Then what changes happened? Did your concentration increase or decrease over time, and by how much? And then the equilibrium would be at the very end, is basically the net of the initial and the change. So let's start with the initial. So initially, it tells us that we have 2 moles of NOCl in 1 liter, so that's 2.00 molar. Your products at the beginning of the reaction are not there. You have 0 products. You haven't started your reaction yet, so this is 0, and this is also 0. The only other number we're given is that 0.66 molar, and that tells us that's the NO concentration, so it goes here, and it tells us that that's the system at equilibrium. So it would go under equilibrium with the NO. So right here, you would put 0.66 molar. Now, if you started initially for NO with 0, and you ended with 0.66 molar, that means that the change was that you increased by 0.66 molar. If we know the change for the NO, we can figure out the change for the Cl2 from the stoichiometric ratio. It's a 2 to 1. So if I increased by 0.66 molar for the NO, then I would increase by 0.33 molar for the Cl2, because that's a positive sign there, because it's a 2 to 1 ratio. And if you look at the NOCl, because it's a 2 to 2 ratio, which is a 1 to 1 ratio, then this would decrease since it's a reactant. It gets used up by 0.66 molar. Then the equilibrium concentrations would be the net of the initial and the change. So you add these 2 together, you add these 2 together, and you add these 2 together. So at equilibrium, this would be 1.34 molar. This we already figured out is 0.66 molar, and then this one is 0.33 molar. Now that you have the equilibrium concentrations, these are the concentrations that you plug into your KEQ expression. So let's do that. So KQ then is equal to concentration of NO is 0.66 molar, that's squared, times the Cl2 is 0.33 molar, divided by the NaCl is 1.34 molar, and that's squared. That ends up being 0.080 is our answer. And again, we don't care about the units for KQ. This number is less than 1, so that tells us that this reaction is reactant favored. That means there are more reactants at equilibrium than there are products. Okay, let's move on to the next one. It says we have 2 moles of H2 and Cl2. They're placed in a 4-liter container. So 2 divided by 4, so half molar for each the H2 and the Cl2. They give us K, it's 1.52. We want to determine the equilibrium concentrations of all substances for the reaction. First thing you want to do, write your KEQ expression. So let's do that. So KEQ is equal to the concentration of HCl squared divided by concentration of H2 times the concentration of Cl2. Okay, well, they give us the KEQ. They tell us 1.52. They want the concentrations at equilibrium, so the equilibrium concentrations of all the substances in the reaction. And they don't give us any of them. They do tell us that we have 2 moles in 4 liters, which is half molar of the H2 and Cl2, but that's at the beginning of the reaction, so that's initial. So in that case, you do an ice chart. So let's do an ice chart. So since my reaction is written right here, I'm just going to do the ice chart under it here. So ICE. So initially, I know that this is 0.50 molar, and this is also 0.50 molar, and that I don't have any products at the very beginning, so that should be 0. I'm not given any other information, so I need to try to figure this out. So I don't have any of the changes, but let's say that H2 decreases by X, since I don't know what amount it decreases by. I don't know what the change is. So I'm going to say this decreases by X, so minus X is my change. Excuse me, if the H2 decreased by X, then the Cl2 would also increase by X, and the HCl would increase, but it would increase by 2X because it's a 2-to-1 ratio from the stoichiometry in the reaction. So then the net, which is my equilibrium, this is 0.5 minus X, 0.5 minus X, and this is, it's a minus there, and that's 2X. So I'm going to go ahead and plug this back in here. So the HCl concentration, that is 2X, but then that's squared. Be careful that the quantity is all squared, so it ends up being 4X squared, not 2X squared. And then divided by my H2 is 0.5 minus X. That's 0.5 there, sorry. And then this one's also 0.5 minus X. And then you solve for X. Now that's pretty hard to solve for. The math is quite difficult there. So what I'd like you to do is, there's different ways to solve it. If you already know how to solve it, that's great. Go for it. If you don't know how to solve it, then go ahead and look at the very back of your packet, the very last page. It gives you 2 different ways for doing it. If you look at the back there, it says how to solve quadratics using graphing calculators. And then it gives you 1, 2, 3, 4 steps, and then it says, or using equation solver. Some of my students told me about the equation solver. I was never able to work it out on my calculator, but it's a much simpler way to do it. So if yours If you can figure it out on your calculator, great, use that. If not, then use the steps 1, 2, 3, 4. That's what I usually use. Or if you know a better way, by all means, please let us know and help us out. Or you can ask your math teacher for help with that. So the way that I do it is I take out my graphing calculator and I plug in, if you look at step 1, it says put for y1. So, when you graph a function, your first function is going to be the quadratic part, and you want to use parentheses for it. So quadratic part means this part, this whole thing. So enter that whole thing into y1. Okay? Then for y2, you enter the number, the KQ value. You enter 1.52. So I'm going to give you a minute to go ahead and enter that into your calculator. So this whole thing goes into y1. Again, make sure you use parentheses there. And then 1.52 goes into the decimal part. Okay? For your window, sometimes you don't really have to change your window. Other times you do. Depends on what your window is already set to. So if you look at step 2, it says set your window for x minimum is 0. X max should be a value that won't give you a negative number for molarity. So, maybe 0.5. Because you can't have x to be higher than 0.5. In this case, for example. Then you want to set your y minimum and maximum so they encase the y2 value from step 1, which is this number right here. Then hit second calc and then number 5, which is your intersection, to find the intersection. So it's going to ask you, is this the first curve? You hit enter, if it's the correct curve. Then it will ask you, is this the second curve? You hit enter. Then it will say guess, hit enter again, and then it will give you the answer. And the answer is obviously the x value is what you're looking for because we're solving for x. So I'll give you a minute to do that if you have a graphing calculator handy. Okay, so I got x to be 0.19 molar. Hopefully you got the same answer there. So then, if you wanted to solve for the concentrations, so you want the H2 concentration, which is equal to the Cl2 concentration. Both of them are 0.5 minus x, which is 0.5 minus 0.19, so that's 0.31 molar. And then you also want the concentration of the HCl, which is 2x, so that's 2 times, 0.19 molar. So that's equal to 0.38 molar. And so we got all of the concentrations. Okay, on to the next page. That should say for special, right here. That's a typo, sorry. For special reactions, we saw that KQ could be called K or KC. KC stands for concentration, KQ stands for equilibrium constant, or just K as the constant. Sometimes, instead of calling it KQ or KC or K, we give it a special name if it's a special type of reaction. For example, let's look at this first one here. We have ammonia and water. Ammonia is a special type of substance. It's a base. So when it's in water, it dissociates, you get NH4 plus and OH minus. And so this is a base dissociating in water. So this is base dissociation. And so instead of just calling it KQ, we give it a special name, we call it KB. But it's the same thing as KQ. It's the products over the reactants raised to their power. So it'd be the concentration of NH4 plus times the concentration of OH minus over the concentration of NH3. Remember, we don't put water in because it's a liquid. So this is the KQ expression, just we give it a special name. It's KB, that stands for the base dissociation constant. What if you have an acid? So let's look at the next one. This is an acid in water. This is acetic acid in water. So you get the acetate ion and the hydronium ion. So this is an acid dissociation reaction. So it's a special type of reaction. And so instead of just calling it KQ, which you can, a lot of times it gets the symbol or the abbreviation Ka for acid dissociation constant. But again, it's the same idea. You take concentration of the products over concentration of the reactants raised to the power of their coefficients. So concentration of the acetate ion times concentration of the hydronium ion, the H3O plus, divided by the concentration of your acid, the HCOOH. And again, we don't include the water because it's a liquid. The next one is really special. This is water. Water is covalent, so it doesn't really have ions that it dissociates into, but because of the extreme polarity of water, a very, a very, 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 very minimal amount of water does dissociate into H plus and OH minus, or H3O plus and OH minus, same thing. And so this is special again, and this is called the water dissociation reaction. Water dissociation. And so again, instead of just giving it any name as KQ, we give it a special name. So instead we call it KW for water. It's the water dissociation constant. But like always, products over reactants raised to the power of their coefficients. So concentration of the hydronium ion, the H3O plus, times the concentration of the OH minus over the concentration, not over anything, just the hydronium and the hydroxide, because water is a liquid, so we don't put it in the expression. So it's just H plus times OH minus concentrations. Next, another special type is when you have an ionic substance, which we call salt. So this the Na2SO4 is ionic, so we call that a salt. This is a salt dissociating in water or dissolving in water. You can call it dissociation or dissolving. So whenever you have an ionic substance dissolving, that gets a special name. We call that KSP. You'll see why in a second. As always, it's the concentration of the products over reactants raised to the power of their coefficients. So concentration of Na plus squared times the concentration of the SO4 2 minus. And then we don't include the Na2SO4 because it's a solid. We don't include the water because it's a liquid. This is called, excuse me, this is called KSP. Stands for solubility product constant. So solubility, the S is for solubility because you have something dissolving, so solubility. Product, because it ends up being a product, it's always multiplied, never divided by anything. There's never a denominator because these are always water, which is a liquid, and then a solid. So we never include a denominator in this, so that's why it's called product. So solubility, product, and then K for constant, so KSP, K with sub SP. So these are all basically KQs. They just get special names because they are special circumstances. So all these Ks are constants. They tell us what the concentrations are, the ratio of concentrations of products to reactants at equilibrium. K is always going to be a constant as long as your temperature is the same. I know here it says pressure and volume remain constant. Actually, don't worry about that. I would cross that out right here. K remains constant at the same temperature. If you change the temperature, K changes. If you change the pressure or the volume, K does not change accordingly. So if you have additional reactants or products, if you change the concentration, K will remain the same. So K remains the same always unless you change the temperature. Temperature is the only thing that will change it.